Hi everyone, this is lecture 26 for hydraulic engineering. Just as a brief reminder of some announcements, please remember that your reservoir sizing submission is due on Monday the 25th. That's our first day back after spring break. So take some time to size that reservoir based on the demands that you've estimated and the peaking factors that you've previously digitized and as shown in class. Remember that if you need some assistance on sizing the reservoir, that there is a screen capture posted of the example solution that I showed you in class several days ago. Also, homework 10, covering chapter 12, some of the concepts that we're covering in this lecture will be due on Friday the 29th of March. Today we're going to talk about chokes. And we've covered some of the basic concepts related to chokes previously. The Froude number equation, as is shown here on the left, tells us that as a function of the channel geometry and the flow conditions, that that combination of variables at critical flow is equal to 1. For a rectangular channel, we can find the critical depth just as a function of the flow per unit width. Well, for the rectangular channel, there's an interesting observation about minimum specific energy, and that is that in a rectangular channel, that the water depth is 2/3 of the specific energy under critical conditions. And as an illustration of that, let's take a look at this example where 50 cubic meters per second is flowing through a 5-meter wide rectangular channel. This example is an illustration of where the specific energy is during critical flow. And in this case, we have a flow rate of 50 cubic meters per second, a channel that has a width of 5 meters. Therefore, the flow per unit width is 50 cubic meters per second divided by the 5-meter width. That gives 10 cubic meters per second per meter of width, or 10 meters squared per second. We can find for a rectangular channel the critical depth pretty easily using this formula, so that it is the 10 square meters per second squared divided by 9.81 meters per second squared to the 1/3 power, and that tells us that the flow depth is 2.168 meters. The velocity is Q divided by A, so that is 50 cubic meters per second divided by 5 meters times 2.168 meters. And so this is during critical flow conditions, the velocity will be 4.612 meters per second. And so the velocity head, of course, is v squared divided by 2g, 4.612 meters per second squared divided by 2g. And the velocity head is 1.084 meters. So the total specific energy is y plus v squared divided by 2g. In other words, that is the 2.168 meters plus 1.084 meters. The total specific energy, 3.252 meters. Now, notice that the specific energy, when conditions are critical, is simply y times 3/2. That is 2.168 meters times 3/2, and we get the same 3.252 meters. That's only when flow is critical. And this expression is a simplification and shortcut that we will use in some upcoming examples. Now let's consider both the step down and the step up as a function of what it does with specific energy. We know that the normal depth of flow leads to some water surface elevation above the channel bed. And in this case, we can see just by looking that it's subcritical conditions because the flow depth is greater than the critical depth. So this is subcritical conditions. The flow is stepping down and specific energy is being gained in this case on the left. However, on the right, the specific energy is being reduced, and this shows supercritical flow because in this case the normal depth is less than the critical depth. Now it's not always the case that there will be supercritical flow when there's a step up. It's just this particular example is supercritical flow and a step up. Alright, let's take a look at the condition where water is flowing in a subcritical condition and there's a step up, some delta Z. At first it's a very small step up. Under subcritical conditions, what we know from the specific energy diagram is that a step up is going to make the flow at 2 shallower than it initially was at 1. Now E2 is E1 minus the delta Z. We can see that visually quite clearly. A bigger step means that there's going to be a reduction even further in the flow depth at 2. So we're getting close to the maximum amount of delta Z that could be tolerated by the flow before choking occurs. And that's where we're at now, some critical point where the flow depth at 2 has been decreasing and decreasing until it gets to the critical depth. Once it's at the critical depth, that represents the most efficient depth for conveying flow over the obstacle. In other words, that's the least amount of energy that is going to be able to get the flow over the obstruction. If the obstruction height gets any higher, then the water depth is going to have to pool upstream of the obstruction for there to be enough energy to get up over the obstruction and it begin to flow at critical depth anymore. So this is the minimum specific energy for that flow rate and channel width. So a step larger than the critical step, this now delta Z sub D, means that initially we had energy 1. The water will pool until it reaches enough energy, E prime 1, that will lead to some new depth, Y prime 1. The Y1 is the before flow depth, Y prime 1 is the after flow depth. And that's how much energy is required to once again reestablish critical flow over the step, so that the total energy will be the step elevation, the water depth, the velocity head, and the flow will back up just until there's barely enough energy to get up over the obstruction, and that most efficient flow condition happens at Y sub C. You'll notice, as per our previous example, that under critical conditions the depth is 2/3 of the specific energy, the velocity head is 1/3 of the specific energy. So here's the specific energy diagram that shows for a certain amount of specific energy, a certain flow rate, a certain channel geometry. We started off with E1, and anytime there's a step up, we're moving to the left on the specific energy diagram along the x-axis because that represents a decrease in the available energy. And so we were at some initial subcritical depth. The step up reduced specific energy and decreased our depth to Y2. We went to even a little bit further for that step B, delta Z sub B. The critical point is the critical depth, but then when we went off the chart, so to speak, the amount of specific energy had to increase until there was enough specific energy to get the flow up over the obstruction again. Let's consider that situation with an illustration where the flow depth is 10 feet over a channel. There's some obstruction, also has a height of 10 feet. And so the water is going to have to pool in order to make it up over that obstruction. And we want to find what is the new flow depth, Y prime 1, upstream where it used to be 10 feet, how high will the water surface have to get in order to achieve flow over that obstacle? We know that there's 500 cubic feet per second, a channel width of 10 feet, the initial depth of 10 feet, and we're going to try and find the new upstream depth. And our process for doing that is to find the total energy required to go over the obstacle. Then we're going to consider whether there's enough energy to satisfy that at 1, and if not, then we'll find out what's the new flow depth that corresponds to how much energy is required. So we're comparing a required amount of energy to how much energy is initially available. Alright, in this example we're going to examine the effect of a choke. Originally there's some stream and the water is flowing at a depth of 10 feet. And then an obstacle is placed, which also has a height above the channel bottom of 10 feet. And so the question is, what is the new water height required to get the water up over this obstacle? So in other words, what will be the new depth of flow to get the water up over this obstacle? And the new depth of flow is y prime 1. And that's the depth of flow required to get the flow over the obstacle. And so in this example we have a channel where the flow rate is 500 CFS, cubic feet per second. The width of the channel is 10 feet. The original depth is 10 feet. And we're trying to find out what's y prime 1. We're trying to find out what's the new flow depth after it starts choking up. Now what we know is that the water will continue to pool until there's enough energy for it to flow at the critical depth over the obstacle. And so it's important for us to understand what is the critical depth. And of course for a rectangular channel like what we have, the easiest way to find the critical depth is with this formula. And so we can put in that the flow per unit width is 500 CFS per 10 feet, and we square that divided by 32.2 feet per second squared as g to the 1/3 power. And so the critical depth, if you're following along doing your calculations, 4.265 feet. Now we remember from the relationship that the minimum energy required, the total energy required to get the water up over this obstacle is 3/2 of the critical depth. In other words, when water is flowing at the critical depth, we know that the depth is 2/3 of the energy. So that 1/3 of the energy is the velocity head term, and 2/3 of it is the critical depth. Therefore, if we find the critical depth, then we can find out the total amount of energy required just by multiplying by 1.5. And so 3/2 times this critical depth of 4.265 gives us a minimum energy required of 6.398 feet. That's the total energy required. Now, here's the water surface. If we were to consider the amount of energy at above the sill. So that is the flow depth and the velocity head above the sill required. And so that's the specific energy required, and the total energy accounts for the elevation above the channel bottom, including the sill. And so that's going to be E minimum, which we've just found, plus the delta Z. And so that's the 6.398 feet plus 10 feet. And so the total energy required, this is the relative to the channel bottom, 16.398 feet. Okay. And so how much energy was there available initially? In other words, we can analyze the situation to find out if there's going to be choking. Now, we can assume pretty safely that since this delta Z is equal to the channel, to the flow depth, the flow depth was 10 originally, and the delta Z is 10, it's going to choke. But just to check, let's see how much energy was there available initially, because if the initial energy available exceeds the amount of energy required, then there won't be any choking. So let's look at initial total energy available. Okay, that will be equal to y1 plus the velocity head term. And of course there are several ways to write the velocity head term. One of them is flow per unit width squared divided by 2g times y1 squared. And so our initial flow depth was 10 feet, and the initial velocity head was 50 feet squared per second as the flow per unit width squared divided by 2 times 32.2 feet per second squared. And then the initial depth was 10 feet. Square that. And so the total initial energy that was available was 10.388 feet. All right, so the conclusion we can draw is since total energy required, which is 16.398 feet, is greater than the initial energy available, which is 10.388 feet, choking will occur. Alright, so the water is going to be pooling upstream, and now what we want to find is the new upstream depth. Okay, so what is that new upstream depth? Well, we're going to ask ourselves what energy is required. How much energy does it take to get this flow up over the obstacle? And so the energy required is going to be this new depth plus the velocity head required to get it up over the obstacle. Remember, y prime 1 is the new flow depth after the water begins to pool. So the minimum energy that's going to get the water up over the obstacle is 16.398 feet. That is saying that we know that there has to be at least 10 feet of energy to get it up over the sill, and there has to be the flow depth. It will be flowing at the critical depth of 4.265, and then a little bit additional energy is required to provide the velocity head. And so this term of 6.398 feet accounts for both the velocity head and the depth. And so the total energy required, I'm just going to say, the total energy required is 16.398 feet is equal to the new flow depth plus the flow per unit width, remember, is 50 feet squared per second squared divided by 2g, 32.2 feet per second squared, times the new flow depth y prime 1 squared. All right. So if we rewrite that again, that is going to be 16.398 is equal to y prime 1 plus 38.820 divided by y prime 1 squared. Okay, and if we turn that into a cubic equation by multiplying each term by y prime 1 squared, then that leads to the equation y prime 1 cubed minus 16.398 y prime 1 squared plus 38.820 is equal to 0. Okay, so now we can put that into our solver or use Excel, some method for finding the roots. And the roots of that cubic equation are negative 1.474 feet, 1.621 feet, and 16.251 feet. Okay, so that's saying that the water is going to have to pool to either this negative flow depth, which obviously is not reasonable, and it's not going to be a supercritical route because the water started off at a depth of 10 feet and it's going to have to get even deeper to get over that obstacle, and so we can rule out the supercritical route. And so this is how deep the water has to be upstream of that obstacle, upstream of the sill, in order to flow over the obstacle. And so once the water has pooled to that level, conditions will once again become steady and things will come into equilibrium. There will be upstream, the depth is 16.251 feet. Here it'll be flowing at the critical depth of 4.265 feet, and of course there will be some velocity head term. You know, this term right here is v squared divided by 2g, and essentially that's the solution here. We didn't actually calculate the Froude number, and so we don't necessarily have to, other than we know that the y1 that we initially had of 10 feet was greater than the critical depth. Remember, we did calculate the critical depth as 4.265 feet, and since that's greater than critical, we have got subcritical flow. So even if we didn't know the logic of it's going to be getting deeper, and so therefore it'll stay subcritical, here we have a confirmation that this is the route of the three that we should select.
Choked flow is when the constriction, whether it's a step up or a pier being added into a channel, or a channel getting narrower where it used to be wide, some sort of a constriction that causes critical flow at that constriction. If the constriction gets higher than the maximum allowable without choking, then the water elevation upstream will pool, and the depth may, the risk of that is that as the water gets deeper and deeper, it can submerge structures that are upstream, and so the pooling can cause flooding upstream because of the obstruction that's put into place. Let's consider this next example of calculating what's the maximum step that can be tolerated before choking occurs. We have a before and after situation. In the before, there is a channel that's 2.5 meters wide with a flow depth of 0.9 meters. This channel is carrying 4.25 cubic meters per second. How high of an obstruction can be put into place and still convey the flow without any choking? We're going to try and find that maximum delta Z, or the delta Z critical, that just begins to induce critical flow over the obstruction.
Okay, in this example there is a channel that has a bottom width of 2.5 meters and the initial flow depth is 0.9 meters. So here in side view is the channel, and there's water in the channel with an initial depth of 0.9 meters. The flow rate through the channel is 4.25 cubic meters per second, and an obstruction is introduced that has a height of 0.05 meters. And so now the question is, what will be the flow depth over the obstacle? Just to do some preliminary calculations, we can find that the velocity initially at 1 is 4.25 cubic meters per second divided by the cross-sectional area, which is 2.5 meters of width times the flow depth is 0.9 meters, and so that gives us a velocity of 1.889 meters per second. The flow per unit width, which we sometimes use, is 4.25 cubic meters per second divided by the 2.5 meter width, so 1.7 meters squared per second. We're going to apply the energy equation. The specific energy equation, to be specific. We've got some specific energy at 1, and that specific energy is going to be reduced because of the obstruction. So E1 minus delta Z is equal to E2. In practical terms, what that means is that we've got our initial flow depth plus the velocity head at 1 is equal to the flow depth at 2 plus the velocity head at 2 plus the delta Z. Just moved it over to the right hand side, so we're adding it now. Alright, our initial flow depth is 0.90 meters. The initial velocity 1.889 meters per second squared divided by 2g is equal to y2 plus 4.25 divided by 2.5 times y2. The flow depth at 2 is an unknown. Plus 0.05 meters is that step height. Okay, so that is 0.90 meters is the flow depth. The velocity head initially at 1.1819 meters is equal to y2 plus 0.1473 divided by y2 squared plus 0.05. We can combine all of those terms together and we'll have y2 plus 0.1473 divided by y2 squared minus 1.0319 is equal to 0, which leads to y2 cubed minus 1.0319 y2 squared plus 0.1473 is equal to 0. Okay, using a solver, find the roots to that cubic equation are negative 3.29 meters, 0.557 meters, and 0.804 meters. So which of those is going to be the new flow depth? Well, to know for sure whether it's the supercritical root or the subcritical root, we have to diagnose what was the flow regime at 1. So at 1, the Froude number was V1 squared divided by GY1 to 1/2 power. Okay, so the Froude number was the 1.889 meters per second squared divided by 9.81 meters per second squared times the depth of 0.90 meters to the 1/2 power. The Froude number at 1 initially was 0.636, and so that is subcritical, meaning that the new flow depth will be the subcritical root of the two that were positive. So y2 is 0.804 meters. What we know is that this obstruction did not cause choking, although it did change the flow depth. The flow depth over the obstacle is shallower than the initial flow depth was. What sort of a flow depth would cause choking? And so what is the max step? We can do that by looking at choking. And so let Y2 is equal to YC. We're going to say when we know that choking just barely starts to occur, the depth of flow over the obstacle is the critical depth. And so we have to find the critical depth. Y sub C is the flow per unit width squared divided by G to the 1/3 power. And that is 1.7 meters squared per second squared divided by 9.81 meters per second squared to the 1/3 power. The critical depth is 0.665 meters. And we're going to use that to find the velocity. The velocity at 2 if conditions were flowing at that critical flow. So flow rate divided by the area. So the thing that we're going for is the choke height that causes critical conditions up over the choke, up over the obstacle. Okay, and so if the flow depth was critical over the obstacle, then the velocity at that juncture would be 2.555 meters per second. Alright, so we'll now look at energy equation. The energy expression is that the flow depth plus the velocity head will equal the critical flow plus the critical velocity squared divided by 2g, and this delta z max. The delta z max is the elevation that gives us just barely starts to cause the choking. Our original flow depth was 0.9 meters, and we knew our original velocity. And the critical depth and the velocity when flow is going at the critical depth. Plus delta z max. And if we solve all those terms for delta z max is 0.084 meters. And so any obstruction taller than that in this channel for this flow rate is going to cause pooling upstream of the obstruction. Anything less, like we saw in the first part of the example, where the obstruction was only 0.05 meters, then there won't be choking.
Here's another approach to trying to find out whether the specific energy is sufficient at 1 to enable flow over an obstacle without choking. We're going to find the maximum allowable obstruction before choking here and find out if it's going to choke or if it won't choke. Again, we have a 10-foot wide channel that's carrying 500 cubic feet per second as per one of our previous examples today, and the initial flow depth is 10 feet. So in this case, the obstruction, instead of being 10 feet deep, is just 3 feet deep.
Let's now consider the case of a rectangular channel, same rectangular channel as the previous example, where the bottom width B is 10 feet, and we've got some flow of 500 CFS. Now, there is a channel, and our initial flow depth is 10 feet. And a sill, an obstacle, has been introduced that has a delta Z of 3 feet. So, will it choke? Let's go through the analysis required to determine whether it's going to choke. First of all, we have to ask ourselves, what is going to be the flow depth over the obstacle? And so first point of analysis is, what is Y2? First of all, we're going to take a look at the energy expression that says the specific energy at 1 minus the delta Z is equal to the specific energy at 2. In other words, however much energy there was here at 1 is going to be however much energy there is at 2, except for the fact that we've got this obstacle, and the obstacle is removing some of the specific energy, and so that's why we subtract delta Z from the E1 term. Okay, so if we substitute in y1 plus v1 squared divided by 2g minus delta Z is equal to y2 plus v2 squared divided by 2g. So this is the specific energy equation that we're going to make some substitutions to. Now, of course, when we don't know exactly what the velocity is, we can write the expression in terms of flow rate. So another way to write this is y1 plus q squared divided by 2g a1 squared minus z is equal to y2 plus q squared divided by 2g a squared, a2 squared. All right, we can substitute in the values that we actually know. The initial flow depth was 10 feet, and the flow rate is 500 CFS squared divided by 2 times 32.2 feet per second squared. And the initial cross-sectional area, because our initial depth is 10 feet, that means that it's going to be 100 feet squared initially as the flow depth, minus this obstacle height is 3 feet as the delta Z, is equal to, well, we don't know what the new flow depth over the obstacle is going to be, y2 plus 500 CFS squared divided by 2 times 32.2 feet per second squared times 10. We know the width will still stay 10, but the flow depth y2 is unknown. Okay, so this simplifies to 10 feet, and the velocity head term 0.3882 feet minus 3 feet is equal to y2 plus 3882 divided by 100 y2 squared. Okay, we can combine terms together and get 7.3882 is equal to y2 plus 38.82 divided by y2 squared, which leads to the equation y2 cubed minus 7.3882 y2 squared plus 38.82 is equal to 0. And through using the solver, the roots of this cubic equation are negative 2.03, 2.961, and 6.457. This is the supercritical root. This is the subcritical root. And we had subcritical flow to begin with, and so this will be our flow depth at 2. So flow over obstacle is 6.457 feet. Now, if we think back to what the minimum amount of energy required is, in a previous example, what we found is that the E minimum is 3/2 of y sub c, and we found that the previous y sub c value was 4.265 feet. And so the minimum amount of specific energy required is 6.398 feet. So we could have known much earlier that it wasn't going to choke, because what we have found is that the amount of energy that's available is going to be the specific energy at 1, I'm sorry, the specific energy at 2 minus the energy removed by the choke is going to be this 7.3882, and so won't choke. There's enough energy for it to get up over the obstacle without pooling. Now, another way to confirm that is that we can find out the Z max. We can find out how high can the obstacle get before choking occurs. So what is delta Z max is another thing for us to take a look at. And for the critical depth of 4.265 feet and an E minimum of 6.398 feet, then the delta Z max is just the energy that's available minus the minimum energy. The energy that was initially available from the previous example was 10.388 feet, and if we subtract the minimum of 6.398 feet, then the maximum obstacle height is 3.99 feet. And since this 3-foot obstacle that's actually in place is less than the 3.99 feet, then we know that the water can actually flow over that 3-foot obstacle without choking occurring. In other words, there won't have to be pooling at location 1 for enough energy to accumulate before it can get up over that obstacle.